Hello, welcome to this video 2-3 on curve sketching. In this video, we're going to talk about some basics and foundational pieces of functions that help us sketch curves or sketch the graph. In the second video, video B on this lesson, we will actually look at some examples and we'll sketch some curves. Okay, so let's go ahead and look at the pieces that we're first going to talk about, and all of these should be kind of familiar terms for you. So one thing we need to consider is domain. And again, when you're thinking about domain, you want to avoid certain values, right? So you don't want your denominator to be 0. And then when we're talking about radicands, you don't want negative values in here. And actually what I should do, I'm going to erase this. I'll write this in red. So this is like a do not do. You don't want that to happen. Vertical asymptotes. Vertical asymptotes come from our denominator restrictions, okay? So in this case right here, if this happens, right, then we get a vertical asymptote, okay? And then we'll look at reducing the function and what happens there. Now, if you reduce a function, again, you have another discontinuity. This is a whole, right? This comes from reducing terms. Okay, so we'll find those. X and Y intercepts, you guys are very familiar with those. We'll look at calculating those. And then end behavior. The last video when we talked about limits at infinity and infinite limits, that's end behavior here. Okay, so what happens is my X values go all the way to positive infinity, and then what happens is they go all the way to negative infinity. I don't know if that was backwards. I think it's backwards on my screen. Okay, negative infinity, positive infinity. All right, even odd, and then even odd, sometimes we'll want to see if a function's even or odd, and this can help us determine just a general shape of the graph. All right, so here are the first three examples that we'll look at, and we're asked to give the domain, reduce the function, find asymptotes and holes, and then talk about the end behavior. So for example 1, x plus 2 over x squared minus 2x. So in this case, what we're going to do, we're going to simplify out the denominator, x minus 2. Okay, and notice, right, I don't want a denominator of 0, so I can set my denominator equal to 0, saying, hey, x, you can't be 0, and hey, x, you cannot be positive 2. Okay, so these are your domain restrictions. Can't be 0, or x can't be 2. And if you want to write this in interval notation, negative infinity to 0, union 0 to 2, union 2 to infinity. That's how you would write it out. All right, so because I have these domain restrictions, right, my denominators can't be these values, we get asymptotes here. We get x equals 0, that's one asymptote, and x equals 2. This is another asymptote. Now, I know these are asymptotes because I didn't reduce, right? If my function here, if I could have reduced any of these factors, then that would be a whole. But due to these discontinuities here, those are pure asymptotes. And it's worth noting too that both of these asymptotes are odd end behavior, right? So my function, they're gonna go opposite directions. All right, do you like that sound effect? Okay, end behavior. End behavior is what happens at the end of a graph. And it's worth noting, right, that we want to calculate the end behavior of a function by calculating the ratio of your leading terms. So here my leading terms are x over x squared, So in this case, right, this is the little over big, and what we're going to get here is a horizontal asymptote at y equals 0. Okay, So that's our end behavior. Our function is going to go out towards the asymptote at 0, and right, the denominator is going to dominate that, okay, and make a horizontal asymptote at y equals 0. So essentially what we have here is the limit as x goes to positive infinity of our function, which is x plus 2 over x squared plus minus 2x, okay, is going to be equal to 0. Now, also the same for the negative infinity direction. So as I approach negative infinity of my function, we're going to go towards 0 as well. Okay? All right, example 2. In example 2, the domain cannot be, let me switch colors. Domain cannot be -3. Okay, and this is because we have an asymptote here at x equals -3, and notice that it is a power of 2, so that's a even, right, asymptote, so both endpoints are going to go up, okay, at that asymptote. If our leading coefficient here was negative, if I had a negative in here, then that would make our function go down at the asymptote. But okay, so they're going to be going up. And then our end behavior. So end behavior in this case, right? So what is the limit as x approaches infinity for our function 2x cubed over x plus 3 squared? Okay, and in this case, notice our numerator is kind of dominating this value, right? This is the big over little, and in this case, our function, right, is going to go, it's going to blow up to positive infinity. Okay, so this is going to positive infinity. So what we call a slant asymptote, where our function is going like this. Okay, and now I know this is positive infinity, and I'm going to do a little sign analysis, because if I plug in a positive infinity up here, okay, I get a positive. If I plug in positive infinity in the denominator, this also is a positive, so we get a positive infinity. Okay, and then last but not least, we'll go ahead and talk about negative infinity. So we get 2x cubed over x plus 3 quantity squared, and in this case, if I plug infinity into the denominator, that's going to be positive, but the numerator is going to be negative, so this is going towards negative infinity. Okay, last example, example 3. Here we have h of x, and if we factor h of x and simplify it into this form, we have two terms that match, top and bottom. Okay, so in this case, I have two discontinuities. I have a discontinuity at -2 and a discontinuity at 2. Okay, now so our reduced function is going to be x plus 4 over x plus 2. Now the vertical asymptote, right, is the discontinuity in the denominator after we reduced. So here x equals -2, okay, and this is odd. It's your vertical asymptote. And then we have a hole. This comes from this portion here, right? The reduced factor is our hole, okay, and so our hole is at 2. And then if we plug in 2 into our function here, we get 6 over 4, which can reduce, if you feel lucky enough to reduce, or good enough to get it right, okay? So there you go. Anything numerical, again, is fine. All right, end behavior. End behavior. So what is our end behavior? What is the limit as x approaches positive infinity for x plus 4 over x plus 2. And again, we're going to look at this ratio here. Notice this ratio is the same power over the same power. So what we do is we just look at the numerical terms. Okay, so the coefficient is 1. Coefficient in the denominator is 1. So this limit is 1. Okay, that's where your horizontal asymptote is going to go. It's going to go to positive 1. Same for x approaching negative infinity. Equals 1. Okay, and this is a horizontal asymptote at y equals 1. All right, so that's it for this video. We talked about the pieces of, I guess, the pieces of the function that are needed for curve sketching, kind of the key features, if you will, right? We talked about that a lot in the accelerated Math 1, 2, and 3. And in the next video, we will talk about actually graphing this information. Catch you next time.